So what we want to do now is we want to look at examples of reflection in plane mirrors. So a plane mirror would be a mirror that's a plane. So it's a flat, your standard flat mirror. In the next chapter, we talk about curved mirrors and how they can focus light and make images. But now we're just talking about a plane mirror. So we know that when light reflects off of a plane mirror, that the index, or rather that the incident and the reflected angles are equal to each other. So now I want to look at a little more complicated situation. So what we've got is we've got two mirrors that are at right angles to each other. So now I have a beam of light, okay, and it's going to be at an angle here that is an angle of 55 degrees from the vertical. And so what's going to happen is it's going to reflect off here, it's going to hit there, and it's going to reflect off there. So what I want to know is for the reflected beam, what angle is that compared to the incident? Well, we look at it and say, well, if this is 55 degrees right here, that means it's 35 degrees relative to the mirror. So that means this is 35 degrees right there. Well, since this is a right angle over here, some of the angles has to be 180 degrees. So that means this has to be 55 degrees right there. So that makes this 55 degrees. If I draw a perpendicular right there, that is going to be 35 degrees. So that's going to be 35 degrees. And so that means that this beam right here is 35 degrees from that. But if these two mirrors are perpendicular to each other, the perpendicular to that mirror is parallel to the other mirror. So that means that this line is parallel to that line. And so if this is 35 degrees and that's 35 degrees, that makes these two lines parallel to each other. So the incoming beam bounces back exactly parallel to the one that went in. Okay. And so this is an example of a reflector. Now this is actually an interesting thing, because what that means is that imagine radar coming in, and so if radar comes in, bounces off, it's going to go right back where it came from. So this is an interesting thing, because that means that anytime you have two perpendicular surfaces, it makes it easy for the radar to reflect back to where it came from. And that was one of the first steps in stealth technology for aircraft, because typically the way aircraft were built since World War I, even before, is you had a lot of perpendicular surfaces on them. You had the vertical and horizontal stabilizers, you had the wings and the fuselage, they all made perpendicular angles to each other. And so what would happen is radar would come in, bounce around, and come right back where it came from. So you'd have a radar dish, it send radar out, it bounce off and come right back. And so this is how you found aircraft, radio detection and ranging. And so that's the whole point of radar. And so the very first step to making aircraft stealthy was to angle all the surfaces so that they did not reflect radar back where it came from. So what would happen is you would angle the surfaces in such a way the radar would come in, bounce, and go off in some other direction. And so that would leave very little radar reflecting back to where you came from. And so that would, like I said, was the very first step in stealth technology. And so modern aircraft, modern warplanes have very few perpendicular surfaces on them if they can avoid it. Likewise, modern naval vessels have been redesigned to have very few perpendicular surfaces on them. And so everything looks very smooth rather than the chunky appearance of World War II warships. So we can now do another example here. We can imagine that we've got a mirror here in which the other mirror is tilted 25 degrees. And so we now can imagine light coming in here at an angle of 75 degrees from the normal. Okay, so that means it's 15 degrees relative to the mirror surface. When it reflects off, it's going to be 15 degrees there. Since this is a 25-degree angle there, that means this angle there is 115 degrees. Okay. Knowing how triangles work, the sum of the angles all have to add up to 180 degrees. That makes this 50 degrees. So that makes this 50 degrees. Okay. So that means that if we imagine here if that's 50 degrees right there, okay, then this angle right there is going to be 40 degrees. That's going to be 40 degrees right there. If we draw a perpendicular right there, okay, then that's 15 degrees right there. Okay, and so that makes this right here. That'll be 40 minus 15, so that'll be 25 degrees right there. And so this angle right there is going to be 65 degrees relative to the parallel to this. Well, this is 15 degrees relative to that right here. That's 65, so the angle between the two is going to be 50 degrees. And so the light comes back at an angle that is 50 degrees relative to the incident by tilting this by 25 degrees. And so that gives you kind of an idea as to what goes on here. Notice this is why we call this geometric optics, because we're doing all this geometry, triangles. Now, the nice thing about the geometric optics is that we really didn't have to do a whole lot of math other than knowing the rules of triangles. And so if you were to, and knowing even incidence and refraction. So if you were to actually draw this and draw it using graph paper and a protractor, and you carefully measured this to be the right angle, you carefully measured this to be the right angle, you carefully measured that to be the right angle, you carefully measured that to be the right angle here, and then you just simply measured the final angle, you'd get the right answer. You don't even have to do any math. You just have to be very careful and then know that angle of reflection equals angle of incidence. And so if you know that and you follow through, then you could actually do this correctly without doing any math at all. Now that's the advantage of this geometric optics and this reflection off of plane mirrors. So that's a fantastic tool. I mean, no math. Now that's and even the math that we did here was not all that difficult math. And so we just had to think back to geometry. This is what gets people in this part of the class, is that instead of doing all the complicated calculus we've done before, we're now doing just simple geometry. And so you have to think all the way back to when you had geometry in school. And so that's what we're doing right now. And so that's what this is all about. Now, it helps if you draw big. Even if you're just doing mathematical analysis, freehanding like I did here is not really the best way of doing it. You do better by just using a protractor, at least trying to draw it close. Because the closer you draw it, the more likely you are to be able to look at it and see if you got it right. So that's just the whole idea here. And so this is way easier than some of the stuff that we've done before. So here we have an example. We have two examples here with plane mirrors.